Okay, is a sampling distribution. The sampling distribution of a statistic is the graph or the distribution of values taken on by the statistic in all possible samples of the same size from the same population. So for example, if we're talking about our statistic is the proportion of successes, then every possible sample you could take from the population, every possible proportion that could come out of those samples would be graphed in the sampling distribution. A parameter is the number that describes a characteristic of a population rather than a sample, like the population mean or the population proportion. And we usually use Greek letters to denote those. It is very important when you do things like writing hypotheses that you remember to use those Greek letters like mu equals 0 instead of x bar equals 0. Big points taken off on the AP exam if you confuse parameters and statistics. So always be very careful about being clear about that. A statistic is a number that describes a characteristic of a sample, such as the mean or the proportion of successes or something like that in a sample. And it is often used to estimate an unknown parameter. So we might use a sample mean to estimate the mean of a population that we don't know the true mean for. Sampling variability is just the idea that if you repeatedly sample from a population, the statistic you measure varies from sample to sample, even though the parameter stays the same. So let's say that in the United States, the proportion of people whose favorite color is red is 30%, okay? And so you might take a sample of your population, and maybe in that sample it comes out and says 25% have red as their favorite color. Maybe you do another sample of the exact same size from the same population. It might say 32% have red as their favorite color. So there's going to be some variation, even though the true mean is not moving around. It's just that we have some variability in our samples. So how do we make a sampling distribution? Well, there's a couple other graphs that we want to distinguish it from, just to be clear. The first is a population distribution. Okay, that is a graph of the parameters in the population. It shows how a characteristic is represented. So maybe if we're doing a graph of all the favorite colors, we would say 30% like red, 20% like blue, 15% like purple, so on and so forth. So it might be a bar graph. Maybe it would be a pie chart if it's out of 100, something like that. Usually we don't know the population parameter distribution. We don't know the true values of the population. So instead we take a sample. The graph of the results in the sample would be a sample distribution. And so that might say that in our sample, 30% liked red, or 28% liked red and as their favorite, and 32% had blue as their favorite, so on and so forth. That could be a bar graph or a circle pie chart depending on what you're measuring. We could then graph the proportion who liked red on a number line, like if that's what we were really interested in, is who has red as their favorite color. We could take a new sample, graph that, put the value we get, 32% red this time, 15% red next time, 18% red, 33% red, 28% red, and start building up a dot plot or maybe even a histogram. That would be the sampling distribution for the proportion of red in the population. So be very careful about terminology. Population distribution versus sample distribution versus sampling distribution. Think of, sampling is a verb, so it requires you to be doing some sort of action. And what is that action? It's sampling over and over and over again. Okay, and so we made some of those in class back when we did chapter 18. Why do we need to know about all this? Well, a statistic is an unbiased estimator of a parameter if the mean of the sampling distribution is equal to the true value of the parameter being estimated. Well, it turns out that if you use good sampling methods, that sample means and sample proportions are unbiased estimators. So making a sampling distribution can give you really good information about what the true population parameter is. So it's a very valid way to try to figure out those unknown parameters that you need for whatever reason. Making sure it's recording here. Okay. This leads us to many powerful inference techniques for estimating and evaluating evidence against hypothesized population parameters. So this whole idea of a sampling distribution is the foundation of confidence intervals and hypothesis tests. Okay, so it's a really important concept. Variability. The sampling distribution is described by the spread of its sampling distribution. So to decrease the spread, we can increase sample size. And that will make our sampling distribution, let's say it's unimodal and symmetric, it'll shrink and become narrower. Okay, so that's one way we reduce variability of a sampling distribution. The ideal situation would be to have low variability and low bias. So a large sample size and random sampling of an unbiased estimator. Sampling distribution for proportions. The sampling distribution for a proportion, we learned in chapter 17, can be modeled by a normal model with the center at the true population proportion and the spread as the square root of PQ over N. If the following conditions are met, the 10% condition, which is really a check for independence, but we're sampling, so we don't have independence. So it's saying that our sample is a small enough chunk of the population that we're not changing those probabilities drastically. And the success-fail condition, which again comes from chapter 17, just saying that NP and NQ are both greater or equal to 10, that our sample size is large enough for the normal model shape to have a chance to take hold. Okay, so sampling distribution for proportions can be modeled by a normal model if those conditions are met. Well, we did inference for proportions. We also did inference for means. So what is the sampling distribution for a mean? How can we model it? Well, according to the central limit theorem, CLT, which is considered like the fundamental theorem of statistics, the sampling distribution for a mean can be modeled by the normal model with the center at the true population mean with a spread of the true population standard deviation sigma divided by the square root of n. Okay, now that's true if the following conditions are met. We have random sampling, and then we have independence and 10%. Okay, so same conditions that you are familiar with. All right. Some of you are confused about terminology relating to all these different, standard deviation, standard error. What is the difference? Okay, well, standard deviation of a sampling distribution for a proportion is square root of PQ over N, but we usually don't know P and Q. They're population parameters, right? It's the number of successes in the population and the number of failures in the population, or proportion anyway. We usually don't know that, otherwise why would we be sampling in the first place? So we have to estimate them usually with P hat and Q hat, our sample proportion of success and failures, and this makes our standard deviation not the true standard deviation of the population, so it's an estimated standard deviation, right? It's not the true sampling, it's not the true standard deviation of sampling distribution, it's an estimate. And so because it's an estimate, we call it a standard error. And so it's just kind of a weird terminology that's still used in math, kind of old, where error doesn't necessarily mean something's wrong. It has to do with it being an estimate, okay? The standard deviation of a sampling distribution for a mean is sigma over the square root of n, but we rarely know sigma. We rarely know the true population standard deviation. So we usually estimate it with the sample standard deviation, S sub x. And that makes the standard deviation an estimate, and so it gets called a standard error. Okay, so when you see SE in formulas and stuff like that, it really just means the standard deviation using the values from your sample. Okay, and it's just an estimate of the real standard deviation that we just aren't able to calculate. All right, that's our overview of chapter 18. I think that's all we need to know. So good luck on the problems tomorrow.